Okay, I'm going to be going over the ideal gas law in this problem and some practice problems. So, the ideal gas law, PV equals nRT. Sometimes we just call it PivNRT for short. PV equals nRT. Pressure times volume equals number of moles times R times T. So we have to know what R is. R is called the ideal gas constant. Ideal gas constant. It's basically a way for us to make this equation work for real life situations. So R, you have to know the value of 0.0821 liters atmospheres over moles Kelvin. Okay. Now there are different values for R. If you look up the value of R, you might find a different one. That's because this number correlates with these 4 units. But these 4 units really could be anything else, and that would give you a different value. A lot of textbooks use, I know they often will use like KPA in here, and that'll give you a different value, but what we're using in chemistry is this value. And this is generally what I've always seen used. So just a quick overview of when we're going to use this gas law. Notice the moles in here, N, number of moles. Most of these problems are going to involve moles. So if you ever see moles in a gas problem, odds are you're going to have to use this one. In addition, instead of giving you moles, I can give you grams, because really by this point in the year, if you see grams, you should know you're going to be converting to moles anyway. So when you see grams or moles of the gas that comes into play in the problem, you're probably going to be using this ideal gas law. That doesn't mean you can forget your other gas laws, though. We had the combined gas law, which was P1 V1 over T1 equals P2 V2 over T2. This one is generally used when you're comparing like before versus after. So if you're like tweaking or changing some aspect of a gas and you want to say like what's the new blank going to be. For example, if you have a certain gas with a certain pressure, volume, and temperature, and let's say you're going to heat the gas up. So you're going to change the temperature. What's the new pressure going to be? So whenever you see like what's the new something going to be after you change one of these, that's when you're going to use a combined gas law. You're usually not going to see any moles in here. Sometimes they'll throw grams or moles in, but if the moles are held constant, it's not going to come into play. So generally, if you don't see moles or if the moles are held constant, you're probably going to be using this gas law if it involves changing a gas. And finally, you also can't forget Dalton's law of partial pressures. P total equals P1 plus P2, etc. That just means that the total pressure is the sum of all the partial pressures. And when you see something involving partial pressure or vapor pressure, or like collecting a gas through water displacement or by bubbling it through water, a lot of times you're going to have to incorporate this Dalton's law in here. Alright, so let's go through some practice problems. So first problem, what's the pressure of a 500 milliliter steel tank that contains 938 grams of helium gas at 25 degrees Celsius? So let's first consider which gas law we're going to be using here. Well, I see volume, I see grams, and now when I see grams, I really think that's going to be moles. So I have volume, moles, and temperature, and I'm looking for pressure. So the hint here is you see the grams, which are like moles. This is probably going to be a PivNRT problem. I also don't see anything about anything changing. I don't see it saying what's the new blah, blah, blah. So this is definitely going to be a PV equals nRT problem. Let's write it out. So we're looking for the pressure. So that's what we're looking for. The volume is 500 milliliters. But keep in mind, when we're using this value of R, you have to use these 4 units. It only works if you use these 4 units. So that means your volumes have to be converted into liters, your pressures have to be turned into atmospheres, and you need moles and Kelvin for your temperature and moles. So for volume, the 500 milliliters, I need to turn that into liters. So this I can do in my head. I can tell this is going to be half a liter. But if not, you can shift the decimal point 3 times, or divide it by 1,000, or really multiply it by 1 liter over 1,000 milliliters. So that's going to be 0.500 liters. 938 grams. We're going to turn that into moles, because you can't plug grams into any of these formulas. You always need moles. So that's going to be N. So 938 grams of helium, this is going to be tons of moles, times 1 mole over, for helium, it's 4.003. And let's see what we get. 938 divided by 4.003. Oh boy, 234 moles. Probably should have run this one to see if it makes sense. Well, there's going to be a lot of pressure in here. Okay, 25 degrees Celsius. Temperature equals, again, this has to be Kelvin, so we're going to add 273 to that, giving us 298 Kelvin. All right, let's plug in our values here. So, PV equals nRT. We're solving for P. So you want to rearrange first. P is going to equal, so we got to divide both sides by V. So it's going to be nRT over V. Let me rewrite it up here now. So pressure is going to equal, N is 234 moles. R is always known, 0.0821 liters atmospheres over moles Kelvin. And T is our temperature, 298 Kelvin. Divided by V, which is 0.500 liters. Let's check our units. Mole cancels mole. Kelvin cancels Kelvin. Liter cancels liter. We're left with ATM. Does that make sense for pressure? Yes, it does. I don't know how much sense my answer is going to make because it's going to be pretty big. But let's see. So 234 times 0.0821 times 298 divided by 0.500. Well, we have quite a lot of pressure there. P equals 11,449.99. This is actually really tricky with sig figs. You have to be careful here. With 3 sig figs, because 3, and you might say, hey, wait, what about 2 sig figs? Well, did we actually use 25? No, 25 correlates with 298, which is 3 sig figs. So don't cut yourself off to 2 because of that. This is going to be 3 sig figs. I'm going to call it 11,400. And my unit for pressure is ATM. Yeah, is that realistic? No, but it's just the numbers I came up with. Okay, 11,400. Now, we have water decomposes into its gaseous elements during the electrolysis lab. What volume of oxygen gas will be formed from the decomposition of 10.0 grams of water at 22 degrees Celsius and 780 mmHg? So, let's see what we're going to be doing here. Notice I give you grams. As soon as you see grams, you should think moles. And as soon as you think moles, you should probably think of Pivner, PV equals nRT. So I say what volume, so we're solving for V. I give you grams, which you turn into moles. I give you temperature, and I give you pressure. So let's work it out. But here's the thing. I asked for the volume of water, but I gave you the volume of oxygen gas, but I gave you water. This is going to be like a stoichiometry problem involving gases. Generally, when you see some kind of opening statement about a reaction, you're probably going to have to write the reaction with a balanced equation. So let's do that. We have water decomposing into its gaseous elements. So we can assume that's liquid water. Decomposing into H2 gas plus O2 gas. So we need to balance it. I see one O here, so let's put a 2 there. O's are now balanced, and then I need a 2 here. So this is the same lab. We've done this one before, electrolysis. So it's a 2 to 2 to 1 ratio. So I say, what volume of oxygen gas? So we're looking for this. Now, X is going to give us moles, but then we're going to turn that into volume. So we were decomposing 10.0 grams of water. So this I could tell is going to be a gas stoichiometry problem, and these always revolve around moles. Stoichiometry revolves around mole ratios. These problems always revolve around moles. So we need to find the moles of water. Once we find the moles of water, we'll plug that in right here. Then we'll take our mole ratio to go to moles of oxygen. And then from there, we're going to use Pivner, PV equals nRT, to find volume of oxygen gas. So we start with what we know, which is 10 grams of water. 10.0 grams of H2O times 1 mole divided by the molar mass of water. You add up 2 H's and 1 O, you get 18.02 grams. And that's going to give us 10 divided by 18.02, 0.555. 0.555, and that's moles of H2O. So I'm going to take my moles of H2O and put it right here. We're going to now use stoichiometry to find how many moles of O2 will be formed, of oxygen gas. So 2 to 1 mole ratio, what am I going to do? Divide this by 2. Notice we don't need to do any kind of limiting excess reactant. Well, if there's only one reactant, there's no limiting excess anyway. But if this were a regular problem with 2 reactants here, if I only give you one of them, you have to assume that the other one's in excess. So I divide this by 2. X gives me 0.277 moles of O2 gas. So I found moles, but now I need volume. So really, the X, I'm really going to call this N, because that's number of moles. All right, so now I have number of moles of oxygen gas. I have 22 degrees Celsius, that's going to be my T. So 22 plus 273 is going to give me 295 Kelvin. And I have pressure, 780. But I can't plug 780 in there. It has to be in ATM. So pressure is going to be 780 mmHg times 1 ATM over 760 mmHg. 780 over 760. 2 sig figs there, so I could really round this up to 2 sig figs if I want. I'm going to go more sig figs and I'll adjust at the end. 1.03 ATM. Okay, so let's work through the math. I'll see if I can squeeze it in down here. I'll write my formula here. So we're starting with Pivner, PV equals nRT. I'm looking to solve for the volume. V equals nRT over P. V equals, so N is 0.277 moles. R, 0.0821 liters atmospheres over moles Kelvin. T is 295 Kelvin divided by P, which is 1.03 ATM. Let's check our units. Mole cancels mole. Kelvin cancels Kelvin. ATM cancels ATM. What am I left with? Liters. Does that make sense for volume? Yes, it does. Okay. 0.277 times 0.0821 equals times 295 equals divided by 1.03 equals 6.51. 6.51 liters. Okay. Next problem. How many grams of carbon dioxide gas are present in a 2.50 liter container at STP? So, grams. Whenever you see grams, you should really think moles. So I'm looking for moles, I'm looking for N. Are present in a 2.50 liter, so that's my volume, at STP. Now STP tells me two things. That tells me that P equals 1 ATM, and that tells me that T equals 273.15 Kelvin. STP. Now this 1 ATM, that's like infinite 1. It's not like 1 sig fig 1. 1.00 repeating. So now I'm looking for N. I'm given V. I'm given P. I'm given T. You can use PV equals nRT for this. You can say PV equals nRT. Rearrange, solve for N. N equals, what's it going to be? Divide by RT. PV over RT. So you would say 1 ATM times 2.50 liters divided by 0.0821 liters atmospheres over moles Kelvin divided by 273.15 Kelvin. But what you should really be doing here is recognizing that at STP we can use that shortcut. And the STP shortcut goes like this. At STP, 1 mole equals 22.4 liters. That's true for any gas. All gases occupy the same volume per mole regardless of their identity, and at SDP, that volume is 22.4 liters. So, what we're going to do here is just use that as a conversion factor. So in this problem, it gave me volume. It said 2.50 liters. I can now turn this into a conversion factor to just get this right into moles. So because it's at SDP, I have 1 mole and 22.4 liters. So liter needs to cancel liter, so let's put my 22.4 down here. And let's go right into moles. 2.50 divided by 22.4 gives me 0.112 moles of CO2. If you had done it this way, I promise you would get the same answer. It just saves you time, so you should use this SDP shortcut. But we're not done yet. I'm looking for grams, so now we just do a little bit of a conversion here. 0.112 grams of CO2 times 1 mole is down here, and we're going to put the molar mass of CO2, which is 44.01 grams. Let's see what we get. .9. 3 sig figs. 4.93 grams. Okay. Oxygen can be generated in the laboratory by heating potassium chlorate. The reaction is as follows. 2KClO3 solid yields 2KCl solid plus 3 O2 gas. What mass of KClO3 must be used in order to generate 5.00 liters of oxygen gas collected at 19 degrees Celsius and 0.998 atm? Okay, so this is definitely going to be a gas stoichiometry problem. I'm asking for mass, so you know you're going to have to find moles, so this is definitely going to be a Pivner problem. So let's consider what we're given. We're looking for the mass of this, but what are we given to start? Liters of oxygen gas. We're given this. So what we're going to have to do, remember these problems all base around moles. Moles are always the central unit of these types of problems. We're going to have to use the volume, the temperature, and the pressure of the oxygen gas to find moles. Once we find moles of this, we're going to use the mole ratio to find moles of this. And once we find moles of this, find grams. All right, so let's see. PV equals nRT. We're solving for moles of oxygen gas, so we're solving for N. N equals PV over RT, which in this case is my 0.988 atm, no conversion needed. V is volume, 5.00 liters. Again, no conversion needed. Divided by R, 0.0821 liters atmospheres over moles Kelvin. And T, 19 degrees Celsius, we have to add 273 to that. So, what's that going to be? 272, no, 292? Let me just check. 19 plus 273, 292. All right, ATM, ATM, liters, liters, Kelvin, Kelvin. That leaves moles as this double denominator. The double denominator, it's like the inverse of the inverse. It's the denominator of this denominator. That means it comes up to the top. You know, if you do something inverse times inverse again, it comes up to the top. So that makes sense. 0.988 times 5 equals, divided by 0.0821 equals, divided by 292 equals 0.206 moles of O2. Okay, 0.206 moles of O2. So let's put that right here. Now I need to see how many this correlates to. So that's like my X. So you can set this up with mole ratios, like a cross multiplying, or you can just say, well, look, it's a 3:2 ratio. That's getting 1.5 times smaller. So I'm going to divide 0.206 by 1.5, and that's going to become 0.137. So I'll do it down here. 0.137 moles of KClO3. Just once again, 3 to 2 mole ratio. How many times smaller is that? It's 1.5 times smaller. So you're going to divide it by 1.5. Okay. Now we just turn this into grams. So we just need to find our molar mass of KClO3. So 39.0983, that's K, plus Cl is 35.453. 3 O's, that's 16 each, which is 48. So a molar mass of 122.55 grams. 0.137 times this answer gives me, with 3 sig figs, 16.8. 16.8. And again, yes, I will use sig figs because the 19, did we actually use 19 with 2 sig figs? No, we didn't. We used 292. So 3 sig figs, 16.8. And my unit is grams. Okay. This is my last problem here. Consider the combustion of butane gas. Now, odds are, if I tell you an opening statement like that, what are you going to have to do? Write the balanced equation. I'm sure we're going to have to do it, so we may as well now. Butane, C4H10. Gas. All right, combustion reacts with O2 gas to form CO2. CO2 is definitely going to be a gas, plus H2O, which is generally a gas as well. Okay, we have to balance. So with combustion reactions, I would say H, then C, then O. So H is first, 10 and 2. So we need a 5 here. But let me look ahead. If I put a 5 there, that's going to be a problem. Because notice I have O2, so this needs to be even. You can only ever have an even number of O's, so I can't put a 5 there. So when in doubt, double everything. So instead of 1 and 5, I'm going to go 2 and 10. So my H's are still balanced, 20, and my O's are now even. Okay, now C, I now have 8, so let's put an 8 there. And now as long as our O's are even, we're in the clear. We just got to add them up. 16 oxygens here, plus another 10, that's 26, which gives me 13 here. 2, 13, 8, 10. Okay. If 32.8 milliliters of butane gas, which is here, at STP, fully combusts, what volume of oxygen gas, measured at 765 torr and 26 degrees Celsius, is consumed? So tricky problem because it gives us different conditions for the two reactants. Okay, so we're going to be figuring out X, which is my oxygen gas, not in moles, but in volume, liters. So we're starting with the butane gas because that's what it tells us. 32.8 milliliters at STP. Because it's STP, use the STP shortcut. So let's start with that down here. So 32.8 milliliters, we need to turn that into liters. 32.8 milliliters times 1 liter over 1,000 milliliters. I can tell I'm just going to shift the decimal point 3 times to the left. 0.0328 liters. Okay, now that's liters of propane. Because it's at STP, I'm going to multiply it by 1 mole over 22.4 liters, which is going to give me 0.0328 times, divided by 22.4 gives me 0.00146 moles of propane. Not propane, no, it's butane. Butane. Okay, so let me change color here. I'll plug this in where it goes. Now this being my butane, I'm going to put that right here. 0.00146. Okay. We're looking to find volume of oxygen gas, so we need to go like this now. How do we do that? It's a 2 to 13 ratio, which is tricky. So you might want to do your cross multiplying here, where you would say 2 over this equals 13 over x, 2x equals 13 times that, and you can find x. But I can also say, look, 2 to 13, how many times bigger is that? Well, 13 divided by 2 is 6.5, which tells me that this is 6.5 times bigger. 6.5 times bigger. So I'm going to multiply this by 6.5. And that tells me x equals 0.00949 moles of O2. So that's how many moles of oxygen gas are created, consumed, being a reactant. So now I have my moles of O2 gas, but it's not at STP. I know the phrasing of it is a little weird, but it says the butane was at STP, but now the oxygen is at different conditions. So we have to consider those. So I'm kind of out of room here, so let's start on the next slide. So N equals 0.00949 moles. For my oxygen, 765 torr, but you can't plug that in. 765 times 1 ATM over 760 gives me, with, how many sig figs here? 3. I'm going to go with 1.01 ATM. And my temperature is 26 degrees Celsius. I can't use 26, so I'm going to say 299 Kelvin. 273, double check. 26 plus 273, yes. Okay. And now we're solving for V. So, PV equals nRT. V equals nRT over P. Let's see what we get. Volume equals N is 0.00949 moles. R is 0.0821 liters atmospheres over moles Kelvin. T is 299 Kelvin. Divided by P, which is 1.01 ATM. Let's check our units. Mole cancels mole, Kelvin cancels Kelvin, ATM cancels ATM. We're left with liters. Does that make sense for volume? Yeah. Let's see what we get. 0.00949 times 0.0821 times 299 divided by 1.01 gives me 0. Now I'm checking sig figs. Let me look back in my original problem for sig figs. I see 3 sig figs, 3 sig figs, and again you might think 2, but no, we didn't use 26, we used 299. So 3 sig figs, 0.231. The unit is liters. Okay? And that's it.